categorize stationary waves with progressive waves. Progressive, those are the waves that move from one point to another, they carry energy, whereas stationary waves are the waves that do not move. They are stationed in one place. Those are the stationary waves. Then we had looked at the crests and troughs, and then nodes and antinodes. Nodes and antinodes. What did we say antinodes were? Antinodes. We talked about antinodes. What did we say? Remember what we said about antinodes? Somebody try antinodes.
Teacher, antinodes we said are a point on a wave where the particles vibrate at maximum displacement.
Yes, the particles vibrate at maximum displacement. While nodes, the particles vibrate with minimum displacement. So you have something like this. Two waves have formed a stationary wave. At this point where they are on the line, these are the nodes, minimum displacement. Then this point here, these are, we put them N, here we say antinodes. The particles here vibrate at maximum displacement. From here up to here, this is N. This is N. This is A. So when you check carefully on this diagram, you will notice what is the distance between. This is also N. What is the distance between A and N? What's the difference between antinode and node? You check on the diagram. Antinode and node. For example, antinode is here, node is here. What's that distance?
A quarter lambda.
It's a quarter of a lambda. A quarter of a lambda. What about the distance between a node and a node?
A half lambda.
A half lambda.
This is a half lambda. You should be able to check what we are saying to see what we are saying, why it is actually the half lambda. Because the node, if you look at this is the first node. This first node goes up to here. This first node, this is the second node. When you compare this gap, here, and then you have another node and another node, this one. That's when you get a full wavelength. From here up here is a full wavelength. This is the first node, the second node. So the distance between the first node and the second node is a half. Then you get another node plus another node, another half. Therefore, you get a full wavelength. They can ask you a question in this form. They say, let us create a question. Find the wavelength. Let us try this question. Find the wavelength if of a wave. Find the wavelength of a wave if its distance. Everybody, you copy this question and work it out together. If the distance between 20 nodes if its distance, let's say if its is 30 centimeters. Let us start with that question. Find a wavelength of a wave if its distance between 20 nodes is 30 centimeters. Everybody be trying that question and see what we can do. because maybe you have forgotten. First node, second node, third node, and fourth node. So these are 1, 2, 3, 4, 4 nodes. If they ask us for the wavelength, how many wavelengths are here in these 4 nodes? I'll start from here. I'll do, this is 1, 1.5. So we have 1.5 wavelength. And if they had given me the distance here, I would have divided that distance by 1. This is like 1.5. But the nodes are 1, 2, 3, 4. There are 4 nodes. So what you do for that number, just put down, maybe you can write down the nodes. There is a formula we said the other time, but you can write down the nodes. 1, 2, 3, 4, 5. Then you just get to know up to 20, because I've said 20 nodes. Then you check from here, because one wavelength is between 3 nodes. This is 1, this is half full. So from here up to here, this is 1. That is 1 wavelength. Between the 3 and another one is here. That's the second wavelength. So you go on doing that up to the 20th. Then you see how many wavelengths you have.
Teacher,
Yes.
me, I got, after doing that, I don't know if I did it well. I got 3.33.
3.23, eh?
3.33 centimeters.
Okay, centimeters. Okay, that is okay. It was recurring, eh?
Yeah.
It was a recurring figure. 3.33.
Yes.
Okay. Any other person? What answer have you got? Any other person? For those who have not tried, just try the way I've just showed you now. And then you see how you can get that. It's a very simple thing. How you can get the answer. Then, Master, you go to part 2 of the velocity. Remember the formula for velocity? Priscilla, what answer have you got? For part A. Bakit, what answer do you have for part A? Sarah, but people have taken long to do that part 8. It's something, I don't know what's happening. It's a very short thing. Even after showing you the technique, you are still not getting the answers. Can somebody maybe type a chat that you have got the answer? Because we are delaying and your data should be used for other numbers, not only for one number. Aliyah, what's your answer? Isabel. I see Isabel, I see Kaigo. If you have some answer, you reply. You're making me over ask for the answer, yet you know I have the answers. You don't know how they reply. You reply that either you have not got the answer or you have got. Shouldn't be one way, it should be two-way communication. Patience, what's your answer? If you want to answer, you unmute and say something, then you mute again. Master, do you have the answer for part 2? For part B?
Just a minute.
Okay. It's only Master who is doing work. I don't know what's happening with other students. What has happened? Lamunu Priscilla, what's your answer? Nasa, Z, Lamunu, Aliyah, Iman, Precious, Shanita. I see Zoom user. Okay, I think we have to do it together because we might not wait for everybody. When we check with the simplest version, the simplest way not to waste a lot of time, you can write the notes. Let me continue with these ones. Okay, let me write it here. I'm going to write the notes for part A. 20 of them. We shall see the formula 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. You don't have to write them all the time, but we are just checking the simplest way to remember how to do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And from the diagram, we say any 12 is half, any 3 is a full wavelength, any 3. So the first wavelength is this. That is 1. Then this one, the next 3 are these. Then from here, so I take 3, 3. This is 1. When you're taking the next step, you start from this one. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And this is between any node and the node. Between a node and a node is a half. So we have some half left. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9. We have 9 and a half. We have 9, that's a 9.5. 9.5 of our wavelength. 9.5 of our wavelength. And this 9.5 is the one that is equal to the distance they have told you, 30. Now, when you divide here, I don't know that this is what must did to get the answer.
I didn't get that. I ignored.
I should not ignore it, it's part of it. So 30 divided by 9.5, what do we get?
3.1.
3.16.
3.16, eh? Okay, so that's how we get such answers for numbers which have nodes. They can ask you for antinodes. It's the same technique. It's the same technique they're asking for. If they ask for antinodes, you do the same method. And then the distance between any antinode and another antinode, this one is also half. The distance between any 3 antinodes is a full wavelength. So whichever way, whether they bring in antinodes or they say nodes, it's the same technique that you have to use. What about part 2? How did you work out part 2? Part 2 was asking for velocity. We know velocity is equal to f lambda. That's the formula for velocity. Now, if this is the formula for velocity, we ask ourselves, out of that formula, what have they given us? For example, one they're asking for velocity, But when you check in part A has given us wavelength. We have wavelength in part A. And in their question, they are telling us the wave has a period of 2 seconds. What does this 2 seconds give us? What does it help us in this question?
The frequency.
The frequency.
To get the frequency.
So how do you get the frequency from the period?
1 out of
Frequency is
1 out of
1 out of t, and then this is 1 out of 2, which is 0.5.
yeah.
And you have to be careful, was the 2 in SI units of time? Was it in seconds?
Yes, teacher.
Yes, if it's in seconds, then you are allowed to use that. Every time I told you the other time in physics, whenever you come across anything that's not in SI, then you must put it in SI units in physics. So now I go back. So frequency, we have seen frequency. The wavelength was 3.16 centimeters. We have first changed it to meters. Why do we change it to meters? Is it necessary?
Yes.
Why?
Yes. It has to be in the SI unit.
SI.
Has to be in SI unit.
Yes. For the answer, somebody was asking me the other time that should we always change it from the answer? From this first part, you can leave it like this in the first part, but when you are going to use it in any substitution, in any calculation, that answer you have got, the moment you are going to use it in any other formula, then it has to be in standard units. So therefore V is equal to 0.5 times 0. Somebody help us multiply.
You get 0.015.
0.15.
8. 158.
What are the units of velocity?
Meters per second.
Yes, meters per second. That's how we work out such numbers. Okay, I don't know why it had taken you so many minutes to do part A. What was the challenge in part A? Because I thought you could just write down all the nodes and just count three of them. Okay, that was something to check out how to manipulate if the question comes in terms of nodes and antinodes. Can we now go to any other question that you want to ask? We said we are just revising, and in our revision, I call upon questions from you and then we discuss them. Hey, somebody was talking about harmonics. I remember someone talking about
harmonics. Teacher, it was harmonics.
Harmonics and overtones.
Yeah, it's the one that led us to.
Oh, yeah. Maybe for those who are, is there a person who is still copying this solution? Because we want us to start on overtones. And these ones you have to be steady. They're not very hard, but you just have to be steady to understand what we are going to do. Because they're just different things. Should I rub off? Okay, silence means yes. Did you discuss the experiment to determine the speed of sound using a resonance tube?
We didn't understand.
No.
No, we didn't.
Sure, we didn't learn.
Okay, it is part of that part. We are going to see something about it. Let us first look at the harmonics. We shall talk about them. For those who don't have understood, we shall still discuss them later because it is one part that students normally fail to understand at first sight. If you for those of you who don't have the notes for but the lenses, notes for lenses, or you can check in New Vision. I think to appear, I gave in the work last week. I don't know what they put this Saturday, but there's some work of lenses, lenses, and when I'm writing for New Vision, I put details. I put pictures, colored pictures. When I was making your book, we didn't have color. We didn't have color. So for betterment of your notes, you can get New Vision and check out that it is always on for today Monday. Today Monday is some work for physics. Senior threes, it is Monday that I put. So if you get some time and your parents can afford to buy a paper and a copy of New Vision, then you can buy for Monday. By the way, all the days have work. It's good you check out those items in the learning items in the New Vision papers. But for physics, I put real notes, so you could check out those notes and read more about them. Okay, to talk about overtones, I'll just simplify it in a very first question. A tone, what's a tone? When you come to this topic, what's a tone? A tone, without wasting a lot of time, it's like frequency. Okay? Frequency. You get what I'm saying? A tone, we shall be referring to a tone as something like frequency. When I speak, my sound has frequency. So I'm making some tones. Now, if you look at overtone and you look at harmonic, we are going to calculate this. We have this thing, but the one we are doing like this, waves in a string. Waves in a string are the ones that move like this. Here I shall have waves in pipes. These ones normally occur in pipes. Waves in pipes. I don't know that somebody has ever seen these guys who play music, making music through a pipe. Even these guys who are doing the band, the prisons, the students who do bands on sports day, they make sound from woo through some pipes. Have you ever seen those people? You ever seen somebody making sound from a pipe? You have never, I think.
Yes. We have ever. For the food.
Some pipes are open, other pipes are closed. So you look at, for example, a closed pipe. A closed pipe is something like this.
Yes.
A closed pipe, it is like this. Closed at one end, and this end is open. Other pipes are open on both sides. Other pipes are like this. They are open on both sides. Now, for us here, we are going to discuss one by one. To bring in the word overtone, overtone is something very simple. If you pay attention, you just understand it at once. Now, when I have this, if my pipe is a little short, I will have a wave like this. These waves come from both sides. It's like this diagram that we drew, that you have a wave that moves from up, then you also have another wave that moves from down. You have something like this, right? It is similar to this. One side, look at this, right? One side is this, the other side is this. One is this, and this one is down, which is down. So it is similar to this diagram. Now, for you who have understood this diagram, Let me draw for you. This is portion. This is 1. This is 2. What does this represent in this diagram? Is it from 0 to 1 or 0 to 2? This shape. When I compare this diagram, this is my 1. This is my 2. This is my 3. When I look at this diagram, this part, what does it compare with here?
0 to 1.
0 to 1.
0
to 1. Now 0 to 1, in terms of wavelength, it is a quarter of wavelength. In terms of wavelength, this is a quarter of a wavelength. Now, if my pipe is long, then this can come down and this one can go up. But now up to there, what does it represent in these numbers? 0 to what? If you compare this diagram with this.
0 to 3.
0 to 3.
0 to 3.
0 to 3. So if it is 0 to 3, what is that wavelength? Let me see. This is half plus a quarter. A half plus a quarter. So this is 3 quarters of a wavelength. Okay. Let me now from that stage, I'm going to show you how we shall use those wavelengths in our calculations. Now, when they talk about a pipe, in physics, a pipe that is open at one end means that the waves do not meet at the open end. These waves, one that comes from down, this does not meet there. What does it mean by not meeting? If a wave, we can't have a wave like this. We can't have a shape like this. This part here, part 1 is correct, but part 2 is not correct. Part 2 is not correct because waves do not meet in space. Where there is space, waves do not meet there. Waves can only meet where the surface is closed. So where this is closed, that's where the waves can meet. But where it is open, they cannot meet. Actually, when they meet like this, they don't stay here, they continue. That's why when I have my pipe like this, they can't stay here, they just continue like this. Then this one also continues like this. So where there is open space, the waves also open. Where there is a closed space, a closed site, the waves close, they come together. Here they open, here they come together. They don't stay here because there was nothing, no boundary, no wall to keep them there. This is a very important statement. You have to understand this one. We are saying where there is a closed surface, the waves meet there. Where there is an open space, the waves don't meet. They just continue until when they go to the surface. So for open, the waves also open. For closed, they close. You have to be careful. Let me show you this. If I have this, is it a right diagram? Is this a correct diagram?
Yes, teacher.
What if I have this? If my pipe is long. Is it a correct diagram?
No.
No.
This is,
No.
why is it not correct?
Waves do not
They
meet
space
in
at the
space.
end and waves don't meet in
Yes,
space.
they don't.
You
they
said
don't-
waves don't meet in space.
They can't meet and stay like this. What they do, they will just continue and go down. Even this will go up. There they can stay there. They always stay where it is open, they also stay open. Where the surface is closed, they close. I want you to first, are you getting what I'm saying in that first part of closing and opening? Because it's what is going to make up the entire topic of harmonics. But now, how many wavelengths are here? Who can tell me how many wavelengths in that diagram? How many wavelengths? Are they 5.5? Are they what? In that diagram, can you count for me the wavelength? Just count these shapes. Each shape is what? Each shape is a half, isn't it? Do you have each shape is a half? So just count.
Yes, yes.
This is 1, 2, 3. So there are 3 halves.
That's 3/4.
3 halves. 3 halves plus this one. This is a quarter. This portion is a quarter. So this is 3 out of 2 plus a quarter. This is 4. 6 plus 1. Okay. So this is 7. So it is 7 out of 4. This is what I've done. I've just gotten it. Each of these shape is a half. 1, 2, 3. So there are 3 halves. 3 halves. But I didn't complete. There was another quarter left. That's why I said plus. Because we're going to use this information in calculations. So I have to know how to get those waves, how to count the waves and manipulate them in terms of the wavelength. We shall reach that stage. I just want to show you what we shall do. Now for harmonics, recall I've not talked about anything like harmonics and overtones, but I was first introducing the shapes, how the shapes are going to move, because the moment you understand the shapes, then those things of harmonics will just be very simple things. Now when I have this, but now somebody show me this. Is this a correct diagram? But this pipe is open on both ends. I have a pipe open on both ends. We said you can have a closed pipe, or you can also have a pipe that is open. But tell me, is it a correct diagram?
Yes.
Huh?
Since it's open. Yes.
It's a
Because
correct
it's an
diagram.
open pipe. It's correct.
It cannot be correct. You have forgotten our ruling. What was
It's
our?
But it's open on both
Okay,
sides.
it's not correct.
How much is wrong?
It's not correct
Where's the
because we have
not
said
correct.
the waves do not meet and stay there where it is open. Like our diagram.
However much they are open on both sides.
So long as there is some open space, they don't stay there. But then they continue and open also. Where it is open, they also stay open. Where it is closed, they close up. That's the perspective. So this is not open. This is not right. So the correct diagram would be this. This is a diagram. Like this one, this side they open, and also this side they open. That's what should be the correct diagram, where the pipes are open on both ends. Have you seen that? If I had a longer pipe, then I would have done like this. Even if I do so many of these, as long as I leave it open on one side, there is no problem. As long as you leave it open, you can have so many of those waves, so many of them, so long as you know that as I'm finalizing this open pipe, also my waves should stay open. As I'm finalizing the closed pipe, my wave should stay closed. Together, are we people together?
Yeah.
Yes, teacher.
Yes,
Now,
teacher.
for those who are following, how many wavelengths are here in this diagram? How many? Here we say these ones were 7 out of 4 lambda. What about in this diagram? How many of them? You have seen the technique I have used for the other one.
6 quarters.
There are how many?
6 quarters.
3 quarters.
6.
Remember we said each of these shape is a half-half. You start from that. Each of these shape is a half-half. How many wavelengths? I'm waiting.
3 out of 2.
1.5.
1.5. Okay,
2 out
let's
of 2.
together.
3 out of 2, yes.
Okay, let us count. This is a half.
Yes.
Another half. A half plus a half, you get 1.
Yes, and then another.
Then this one is a quarter. Even this side we have a quarter, isn't it? We have a quarter this side, a quarter. So 2 quarters. What do they give? They give a half. 2 quarters give 1 half. So 1 plus a half, 1.5. Or you can say 3 out of 2. It's just fractions. It is 1.5. We can say 3 out of 2 of lambda. Okay, that is, we said that is going to come in when you start the calculations. But now, let us introduce the word harmonic and the overtone. After knowing how to draw those shapes, because it's the shapes that are going to guide us on what we mean by the harmonics and overtone. We can start with the closed pipe. Close at one end. By the way, I have not drawn for you this. Sometimes you can have a pipe that is like this, closed on both sides. What will be the first shape we shall draw?
Close.
We close on both sides. Because it's closed on both sides, so we shall also close both waves, either end. Remember, for this one, for open on both sides, we open on both sides. Remember, for close at one side, we close one side and we open the other side. You see those diagrams, eh? Now, these diagrams I have drawn in each of these pipes. These are the beginning shapes, like the shapes you start with before you build on other shapes. In this one, we start with this. If your pipe is long, it is from this one that we start building others. For this one, it is from this that we start building others. So there is a shape that you start with, that on that shape you build on others which are similar in the same shape. Like here, this guy's next shape, if the pipe was long, would be this. The next one will be like that. So this is the first, this is the second. When you come to this, this is the first, and this is the second. Okay? There is the first and second. Now the first shape is given at is the tone. That first shape in all the pipes has a special name. The special name that we give to the beginning shape, the one we start with, is called the fundamental. Okay, we can say fundamental tone, but first shall call it fundamental frequency. Is the fundamental frequency or fundamental tone. Fundamental tone or fundamental frequency is the first shape that you start with. Now, after this first shape, in our topic of harmonics, it will be called the first harmonic. It is the first harmonic. This is the beginning shape for open on one side. So this is the first harmonic. And its frequency is a quarter of lambda. And we shall give, sometimes we put a 0. First harmonic refers to the beginning shape in that type of pipe. The one that you begin with. We said when it is closed at one side, you close. When it is open, you open. So to this one, you can build on others, but this is the beginning. So the beginning shape, the beginning frequency is called the fundamental frequency. And its special name is what we call the first harmonic. So the word harmonic just refers to frequencies made by a pipe. Harmonic doesn't have a special statement. Like harmonic is the frequency of a pipe, of a tone. Now let us first build a second harmonic. A second harmonic. Let me just extend my pipe a little. Now from this one, when it was like this, I just added, I opened. I'm chasing the open ends. So I had this first one, then I have the second opening. The first opening was here. The second opening is here. So in this diagram, now we have, this is the first harmonic,